Hey, hello, workshop students. Let's go through a couple questions I got. Let's see. I guess it's related to this problem, and I guess it's number 4 on the quiz, and it looks like it's copied to me in little pieces. Let me start again. Here it says a pool ball is struck with backspin as shown in the video. There is a non-zero kinetic friction coefficient between the ball and the table. Check all of the following quantities that change. All right, so that's going to be the key. What is changing during the ball's motion due to friction between the ball and the table? There may be more than one correct answer. All right, so let's talk about the conservational quantities we've been talking about. I'll go back to the first one we did, which is energy. And so the energy one then says that, if there's work done, there is a change in the kinetic energy. So if you had this ball here, and I'll put this as the table surface, and then kind of show a cue stick kind of pushing down and hitting below the center of mass, this would create what they call backspin. So the ball would start moving this way, but it would be spinning with a direction that is opposite. Anyways, that would make a lot of rubbing right here. And so this is the key to the problem. There would be some friction. And the friction is a force. And there's a force, there's a distance, and so there's going to be a change in kinetic energy. So definitely we have a change. Well, I'll just make a list up here, I guess. Kinetic energy. So kinetic energy is going to be one of them. Now, another one we did is momentum. Momentum, or at least a change in momentum, was adding up a force over a given amount of time. And so if you have a force over some period of time, you're going to get a change in momentum. And again, I guess I would say the same thing is happening here. So in other words, as this ball is moving to the left here with this backspin going on, it's going to slow it down, so it's going to lose its kinetic energy. And of course, as it slows down, it's going to lose linear momentum. Now, the more interesting one, and the one that makes this kind of a hard problem here, is the change in angular momentum. And following the analogy of translational motion to rotational motion, there's a change in angular momentum when there is a torque over a period of time. And torque is a little more complicated than force. You have a force and a distance. And since a distance is involved, it has to do with where you pick your origin. Because if you had something that looked like this, maybe just keep it kind of simple. What if I had a bolt here and I put a wrench on, it's a terrible looking wrench, but put a wrench on that bolt. If you apply a force, then there is a distance from its pivot point. But if you were just to grab the center of the bolt and push on it, then you would have no distance involved. So where that force is applied, or put another way, how you're calculating the torque, because if you have something that has no distance from your pivot point, and you could pick an artificial or real pivot point anywhere you want, your R could be 0. All right, well, I hope that wasn't too long-winded, because that's really kind of the key here to our options. And so right here, when it says the total angular momentum, actually, let me go to the easy one first. Total kinetic energy of the ball. Yeah, so this one should be checked, because there is definitely, that's the first thing I said, a change in the kinetic energy. And there's also a change in the linear momentum. That's got to be true too. That's kind of what we were just talking about here. Okay, and so the person who answered this one, total linear momentum, is checked, and that one's correct. What's interesting here is notice 1 and 2 says total angular momentum of the ball around above the ball, and says here is around the origin of the center of the ball, and here is one on the surface of the table. So if we take this as the ball, and here's the surface of the table, and reminding ourselves that this is the force of friction, if you pick an axis that is at the center of the ball, then there would be a torque because there is a distance involved. And when there's a torque, there would be a change in an angular momentum. So around the center of the ball, this one should be checked also. Definitely going to lose angular momentum as measured from the center of the ball. But here, the total angular momentum of the ball around an origin on the table's surface, this is where, again, the force actually acts. This is a force kind of at the rotational axis, and therefore your R is 0, therefore there's no torque, and if there's no torque, there's no change in angular momentum. So this one should not be checked. All right, so hope those help. Take care.